faster you move,
Yeah.
slower
That's
time
what you
takes
just said, yeah.
for you
Yeah.
as seen by others.
Right.
As you approach the speed of light, time continues to slow down.
Yes.
Time travel appears frequently in popular culture, with several time travel storylines in films, television, and literature. However, it is a remarkably old idea. One may argue that Sophocles' Greek tragedy Oedipus Rex, published almost 2,500 years ago, is the first time travel story. But is it possible to travel back in time? Given the concept's popularity, this is a legitimate question. There are various conceivable answers to this question for a theoretical physicist. Not all of them are contradictory. There are two ways to travel through time: going forward or going backward. As you view this video, there are people going through time in the future. Due to the universe-ending paradoxes, time travel can be a bit more challenging. New study indicates, however, that time travel in both ways is not only plausible, but also safe. The question is whether you would do it. At its most fundamental level, time travel is all about velocity, space, and gravity. For instance, a second for a person standing on Earth will differ from a second for a person traveling close to the speed of light or in the vicinity of a black hole. According to mathematics and physics, even if we lack the technology to travel so quickly, this is how time works. We all travel in time. For example, we go 1 year forward in time between birthdays, and we all go through time at roughly the same rate, 1 second per second. Time dilation, a feature of Albert Einstein's special relativity, describes how the rate of motion modifies the relative sizes of mass, time, and space. Einstein was the first to recognize that time is not constant, but rather slows down as you travel faster across space. What this means is that time is an illusion that changes depending on who is looking at it. If you could move at the speed of light, you would perceive time to pass considerably more slowly than it would for someone who remained at rest. Even astronauts in space age more slowly than those on Earth. In order to time travel, it is crucial to know how space-time functions. Albert Einstein's general relativity is the foundation upon which our knowledge of time and causality rests. Einstein had to reimagine space itself. Thus he came up with the term space-time to describe the merging of space's three dimensions with time's single dimension. Einstein envisioned a curved universe with gravitational dips or gravity wells forming around big astronomical bodies like planets, stars, and gigantic collapsing stars called black holes, rather than a flat and rigid space. Not only does gravity warp space-time around black holes, but it does so in any gravitational field, including Earth's. Knowing this is crucial because as you move away from a gravitational source, time will pass more quickly from your perspective. However, it's plausible that there's something else out there that warps space-time as well. Black holes are inescapable voids in space that have been studied by several scientists, including Albert Einstein and Nathan Rosen. In theory, they found that a black hole's surface may serve as a passageway leading to another region of space. This phenomenon became known as an Einstein-Rosen bridge or wormhole. Einstein's theory of general relativity makes the creation of wormholes quite simple. It is thought that these tunnels link two distinct locations in the cosmos. Wormholes may not only link space though, they may also connect different places in time. To be clear, no wormholes have actually been discovered, but research suggests that not only are they feasible, but they may be more prevalent than we realize. When discussing the cosmos, it is essential to understand that space and time are intimately interwoven. In reality, space and time are sometimes regarded as a single quantity known as space-time. A massive amount of gravity may collapse space-time in on itself and connect two extremely distant sites, allowing for nearly instantaneous travel. If this is the case, then the wormhole may have the identical effect on 2 points in time. If it is feasible to go via a wormhole without being crushed by gravity, ripped apart by interdimensional turbulence, or wiped out by an unknown force, then time travel may be achievable by entering one end of a wormhole and exiting the other. A space-time tunnel can also be created by simply connecting a black hole to a white hole. Here's the lowdown on white holes for those who are unfamiliar with the term. Astronomers are attempting to determine how and whether white holes might emerge in the universe. Theoretically, a white hole is thought to be a time-reversed black hole, an area of space-time where matter would arise and spew out light and matter, rather than capturing and compressing matter into a singularity as a black hole does. If it is the exact opposite of a black hole, we should be able to detect it by the many forms of light or radiation it emits. Some experts suspect that some of the black holes we've discovered are actually white holes in hiding. A wormhole's existence would need strong gravitational forces and a significant dilation of space-time. For this reason, some scientists suggest looking for wormholes in the vicinity of supermassive black holes, like Sagittarius A, which resides in the heart of our Milky Way galaxy. Both Einstein and Rosen kept digging into the concept of wormholes, but they ran into some serious obstacles along the way. The first difficulty is that, according to general relativity, the wormhole would close down if ordinary matter travelled through it. Because of this, some form of exotic negative matter would be required to create a wormhole that can remain open permanently. The second concern is that the procedure required to make the wormhole and locate the exotic negative matter to stabilize it must adhere to the laws of physics as we currently understand them. The cosmos does not appear to contain negative matter, yet this does not imply that it does not exist. To maintain a wormhole, the traveller would need to encounter an area of negative energy that would counterbalance the traveller's positive energy mass. That seems almost as implausible as time travel and wormholes themselves. In 2017, however, researchers discovered a mechanism to keep wormholes open using quantum entanglement. This unusual characteristic of entanglement would supply the negative exotic matter necessary for wormhole stability. Since a wormhole has never been discovered, this is an intriguing concept. Moreover, if wormholes are real, they would be very unstable. As soon as a wormhole emerges, it would immediately collapse, or its gravitational force would rip it apart faster than the speed of light, rendering it most ineffective as a shortcut between locations in the universe. But suppose a wormhole appeared and was close enough for us to investigate, and we had the spacecraft. Could we survive a wormhole journey? Nobody knows right now. Of course, no one knows whether or not travelling via a wormhole is a one-way trip. You may never return. And by the time you do, depending on how long you were gone, there may be nothing to return to. You'd also have to contemplate the possibility of never seeing anybody you know again. Some scientists argue that it is possible to send a human being through a wormhole where they would not only survive, but also be able to travel the whole Milky Way galaxy in a single second. While for those who did not go through the wormhole, hundreds of years would pass. But without wormholes, is time travel possible? Yes, if you're talking about moving forward in time. However, it would require a tremendous amount of energy and speed to pull it off. Now, would you be interested in travelling to the year 3000? It may not be as hard as it appears. In reality, small-scale time travel occurs every day, and one astronaut now holds the record for time travel. Yes, you heard that right. However, do not get too excited. When Gennady Padalka returned to Earth after 879 days in space, the planet was 1/44th of a second in the future of what he anticipated. Hardly a fitting plot for a sci-fi film. Nevertheless, it proves in real life Einstein's theory of general relativity, which asserts that time is not fixed, but rather dependent on speed. He also suggested that gravity slows time, implying that time would pass more quickly in space. Astrophysicists such as Richard Gott of Princeton University believe they know how to construct a time machine that might carry you considerably deeper into the future than Padalka's meagre record by travelling much faster than his 17,000 miles per hour. On a subatomic level, this has been accomplished. The Large Hadron Collider accelerates protons to 99.99% of the speed of light, sending them into the future. Conceptually, it is possible to perform a comparable procedure on humans. To reach Earth in the year 3000, all that is required is a spacecraft capable of travelling at 99.99% of the speed of light. For instance, if you choose a planet a little less than 500 light years away and travelled at 99.99% of the speed of light, it would take you around 500 years to get there and another 500 years to come back. So you would return home in 3022. Since you are travelling so fast, however, your internal clock would be moving at only 1/100th of the speed of the clocks on Earth. As a result, you would only perceive the journey as 10 years and would age accordingly. Currently, technological constraints prevent us from realising this prospect. The Parker Solar Probe, which can travel at 0.00067% of the speed of light, will soon be the fastest spacecraft ever created. To propel a starship at nearly the speed of light would also require a massive quantity of energy, which is not provided by any fuel we now use. Additional obstacles would threaten the astronauts' safety and capacity to travel as far into the future as possible. However, these obstacles are easy to overcome in theory. As a race, we still have ways to go before we can truly grasp how time and gravity work. Eventually, humanity may discover a way to travel at the speed of light, or we may locate a wormhole near enough to send astronauts through to explore its inside. There are a few significant takeaways from time travel. Theoretically, travelling to the future is simple. All you need to do is go remarkably fast. Travelling to the past is difficult and requires advanced mathematics, a lot of gravity, and technology that we do not yet have. Not to add that travelling back in time could end the universe if paradoxes do not naturally solve themselves. Would you be bold enough to sign up for such an adventure? Tell us in the comments section.